Yes, hey, welcome back. And yeah, until I find any other good algorithm, it is back to grinding BSc, Need for or Geek for Geeks or whatever it makes my mind. And yeah, today let's solve word ladder one. And again, the question is pretty straightforward. You will be given a word list. You will have a start word and a target word, and you have to take the start word and you have to tell if you can like how many steps it takes to convert the start word to the target word using only the words in the word list. I hope you understood what that means. Let me get into the font. So that means that take DER, like yeah, and they are given some conditions for here, like word will consist only of lowercase letter, so you will not worry about that. And this is the most important thing. These two, like only one letter can be changed at each transformation. In other words, the given word and then next word which you have to check should be in the edit distance of one. So what edit distance means is that how many, like what is the distance which it takes to convert the current word to a given word. So for example, DES and DER. So just by converting S to R, we'll get the actual word, like we'll get DER. So the edit distance between DES and DER is one, but the edit distance between DES and DFR is two, because to convert DES to DFR, first we have to convert E to F, which will be at a distance of one, and then S to R, which will be at a distance of two. So yes, you have to like yeah, only by checking all the words which have edit distance of one, you have to tell how many times, like how many steps it takes to convert the start word to the end word. And yeah, the question is actually like pretty easy to solve. Only if you like identify like under what category it belongs. And yeah, this is believe it or not, this is actually a graph problem. And first time when I saw, I did not even guess it was a graph problem. I only understood it because of what you tell the topic tags. Only on seeing the topic tags and seeing that it is a graph and BFS solution, I BFS problem, I understood okay what to do. And yeah, when you get to know that it's a graph problem, it becomes very easy to solve. So what we'll do is we'll take the current word or start word and put it inside a queue, and like go through our word list and add all the words in the word list which have a distance of one from the start word, and then again start from our queue, pop out the topmost element in the queue, again go through our word list and add all the words which are at edit distance of one from the top of the queue. And when you repeat it like n times, like how many times it takes to find the output, you will actually get the output. That is pretty obvious, I think. And yeah, let's first do that. Like so, I think yeah. That's why I tell always, like knowing BFS is very important. I always tell know level order traversal. Even though it does not come here, just like know how to do level order traversal. So first let's import queue. Yeah, and queue is from collection. So import queue and you get DQ. Yeah, we'll have the start word. And the current distance between start word, yeah, consider D, it was the end word was DER and DES, like the current word was GS and the end word was GR. So that means it will be an edit distance of one, and you'll find it in the next move itself. So we have to actually start from one over here. And so one more thing is that when you check for DER, and when you're like searching for the words which are at edit distance of one from DER, you obviously don't want to check DES because you'll be stuck in an infinite loop. So first you'll check DER, then you'll check DES, then you'll check DER. That will again happen and happen and happen. So you don't want that. So what we'll do is once we have checked a certain specific word, we'll not check it again. So yeah, only one thing should come to your mind when you think of that, and that is a hash like hash set for seat. Yeah. And so what we have to do while queue exists, pop out the current word and the current count or current distance which you have traveled. So current word comma the count. So yeah, let's get rid of base cases first. So if the current word, if it becomes equal to a target word, that means it is like super pretty obvious that we have actually reached our what do you tell destination. So return the count. And uh, yeah, I think that's a meditation issue. Yes. And one more base case is that if the current word actually exists in our visited, That means continue. You obviously don't want to repeat DES, DER, DES, DER. That makes no point. And after checking each word, so add the current word. And now what you have to do, go for each word in that word list. So for each word in the word list, so what you do, like there are only two things to check. Again, if the word actually exists in our visited, that means that there is no need for us to actually visit it again. So if the word exists in visited, then there is no need for us to visit. So we'll just make it. If the word does not exist in visited, only then you have to check. Or the word should be valid. So what valid means is that the word should be at an edit distance of one. So when we are checking for DER, again I'll tell DER should be an in edit distance of one from DES. So it should continue like that. Yeah. So you'll take start word is GEFK and end word is G. So what you'll do, you'll take GFK, add it to the queue, and check for all the words which are at edit distance of one. So you'll check GEK, yeah, and you see that GEK is at an actual edit distance of one, because when you convert E to F, it will actually become Geek itself. So we have to do that. So only if the word is valid, and you have to check it with the current word. Only then what you do, Q dot append the word which you are checking and the count. But obviously, I traveled one step, so count is equal to one. And after doing everything, if you could not reach the result, that means that you cannot actually transform the current word to the, like you can't transform the start word to the direct word, so that directly return zero. So now let's just fill up our is valid function. We'll get the word and the cur word. Yeah, again, just to check for edit distance of one, what we'll do is we'll start a loop from G and check if G is equal to this G, and then we'll check if this E is equal to this E, and then we'll check if this E is again equal to this F. But it should be pretty obvious that E is not equal to F. That is, I don't know, it's not even maths, it is common sense. So this is not equal to F. That means that we'll increase the count. And yeah, the only caveat is that count can actually be one, the edit distance can actually be one, but only if the edit distance is greater than one, you have to return false. So let's declare our count first. Yeah, for I in range, okay. So if the word at position I becomes equal to the current word at position I, that means that we have to continue. So if it is not equal, then what you have to do? Increase the count by one. And if the count becomes greater than one, that means that it was at an edit distance of it was at an edit distance which was greater than zero. Return false. RE, yeah, don't forget to add C and add D. Or else what you have to do, you have to return count. And yeah, if you think that this is correct, then you are absolutely wrong. This is not correct. Why? Because if the given word and the current word are same, so when you are checking for DES and when we again check for DES, what will happen is that, yeah, first it will go over here. It will tell, okay, DES is not actually visited, so we'll add visited. We'll add the current word to the DES, and we'll go over here, and we'll check if the current word is actually equal to the word, and both the words are DES, and this will actually return true. If you do return true, yeah, this will actually return true itself, but it is not actually true because we don't want to check the same word again and again. So only if the current word is at an edit distance of one. Only if the current word is at an edit distance of one. In other words, only if the count is one, then you have to return true. So what this will do is this will directly return true only if the count is one, and if the count is equal to zero, then it will directly return false. And by now, yeah, it should be ready. Let's just compile it once to check if we have made any errors. Okay, if it is taking this much time, that means that we have obviously messed up somewhere, or maybe my network is slow. Okay, not or over here. I think that is the error. Yeah. Both the conditions should be true for us to append. I don't know why I typed off. Yeah, and we got our expected output to be equal to our actual output. So just let's just submit it and check if our actual validation is good, like actual core logic is correct. And yeah, it passes. And yeah, I think the only hardest part in this entire problem is like guessing that this is a graph problem. You would like never guess in your wildlife dreams also that it is a graph problem. But when you get to know it's a graph problem, it becomes very easy to do. So just put it in our queue, pop out the current word, check if the current word is equal to the edit distance of one, and if it is equal, then append it. Yeah. If you know it is a graph problem, the difficulty goes from hard to very not very easy. It will become like very medium, like easy medium. But if you don't know it's a graph problem, it obviously becomes extremely hard to solve, and you will never get to know what to do. And yeah, that's all for it. Thanks for watching, and see you. Grand more DSP.